Tesla has led the way in lithium batteries, but now a new plastic battery is challenging that position. The PolyJoule battery can be charged up to 12,000 cycles, 6 times more than Tesla's 4,680 battery, and can discharge 1 megawatt in just 10 seconds. Made from up to 99% recycled plastic, this battery is both lighter and more environmentally friendly. How will this new battery replace lithium batteries in the future, to the point that even Tesla must pay attention? Before we begin, please help us reach 8,200 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Model Q, Tesla EVs, and the latest news. How do plastic batteries work? The technology behind PolyJoule, a name increasingly mentioned as a breakthrough in energy storage, deserves close attention. To understand why PolyJoule holds such potential, we first need to grasp how batteries work. Essentially, a battery is a device that converts chemical energy into electrical energy. It consists of 2 electrodes, a positive electrode cathode and a negative electrode anode separated by an electrolyte. When connected to an electrical circuit, electrons flow from the anode through the load to the cathode, creating an electric current. Battery performance depends on 3 main factors: power density, energy density, and capacity. Power density indicates the rate of electricity delivery. Energy density reflects the amount of energy stored per unit volume or weight, and capacity represents the total amount of electricity the battery can hold. Common batteries today, like lithium-ion batteries, typically use metals for electrodes. This helps achieve high performance but brings several issues: high cost, heavy weight, fire risks, and environmental pollution. Moreover, their performance gradually degrades after several charge-discharge cycles. PolyJoule takes a completely different approach, replacing metals with electrically conductive polymers or simply plastics. Plastics offer clear advantages. They are lighter, cheaper, non-toxic, and chemically very stable. Thus, PolyJoule batteries can transmit electricity quickly while ensuring high safety and durability. Although metal-free, these batteries still maintain impressive energy densities, opening great opportunities for large-scale energy storage systems in the future. This is why PolyJoule is attracting attention as a smarter and more sustainable alternative in the post-fossil fuel world. Typically, plastics are polymers, meaning their structure consists of long chains of repeating small units called monomers. These monomers mainly comprise carbon atoms combined with other atoms like hydrogen, oxygen, or nitrogen. Because of this structure, pure plastics are usually insulators. They do not conduct electricity. However, when mixed with certain elements or compounds capable of donating or accepting electrons, plastics can be transformed into conductive materials. This doping process generates charge carriers such as free electrons or holes, allowing electric current to move along the polymer chains. This results in 2 types of conductive polymers: P-type with holes and N-type with electrons. By joining these 2 types together, polymer diodes can be created devices that allow current to flow in only one direction. Using many such diodes, people can make plastic solar cells the foundation for polymer-based batteries in the future. PolyJoule exemplifies the application of conductive polymers in energy storage technology. Instead of using metals for electrodes like traditional batteries, PolyJoule employs different types of conductive polymers. The basic structure of the battery includes 2 polymer electrodes placed opposite each other and separated by an electrolyte layer. Each electrode is made from a different polymer to optimize performance. The positive electrode often uses polymers with strong electron affinity but low ion affinity, such as poly-3-hexylthiophene, abbreviated as P3HT. The negative electrode anode uses polymers with high ion affinity but low electron affinity, like polyethylene oxide PEO. Between the 2 electrodes is a polymer electrolyte such as polyethylene glycol, which conducts ions but not electrons, and usually contains salts that can dissociate in water, facilitating ion transport between the electrodes. During charging, an external voltage causes electrons to move from the anode to the cathode through the external circuit, while ions from the electrolyte move into the electrodes to neutralize charges. This process makes the anode more positive and the cathode more negative. When discharging, the chemical reactions reverse. Electrons flow back from the cathode to the anode through the electrical device, like a phone or laptop, generating usable current. Ions in the electrodes also return to the electrolyte, restoring the system to its original state and preparing it for the next cycle. A key difference between PolyJoule batteries and traditional metal-based batteries lies in energy performance, safety, and weight. With an energy density that can reach up to 1,000 watt-hours per kilogram, 4 times higher than the approximately 250 watt-hours per kilogram of current lithium-ion batteries, PolyJoule allows for much greater energy storage in the same weight. Thanks to its lightweight and non-flammable materials, this technology is not only suitable for personal electronic devices, but also holds great promise for large energy systems and electric vehicles, fields that demand batteries that are efficient, safe, and durable. Once again, please help us reach 8,200 subscribers. This is important for us to stay motivated. Thank you. What is the actual cost of the PolyJoule plastic battery? Despite many advantages in safety and durability, one current limitation of PolyJoule is its relatively low energy density, only about 60 watt-hours per kilogram, nearly 5 times lower than the lithium 4680 battery. However, this results in a significant weight reduction. While each 4680 cell weighs around 355 grams, a PolyJoule battery weighs only about 71 grams, just 1/5 of the weight. In terms of cost, this is a notable strength. Currently, PolyJoule batteries are priced at approximately $65 per kilowatt-hour, less than half the price of the 4680 battery, and much cheaper than the average $132 per kilowatt-hour cost of widely used lithium-ion batteries on the market. If in the future the price can drop below $20 per kilowatt-hour as experts expect, this would be a true revolution in energy storage, especially since this battery can be recycled up to 99% and has a lifespan of up to 30,000 cycles, equivalent to nearly 100 years of use. To put it simply, at the current price of $65 per kilowatt-hour, users only need about $325 to own 5 kilowatt-hours, enough to power an entire house, including air conditioning, for about 1 hour. With $6,500, one can build a 20 kilowatt-hour storage system that provides continuous power for nearly a whole day. If these figures are accurate, PolyJoule offers an attractive solution for home energy storage, affordable, safe, and efficient. Technically, PolyJoule uses electrodes made from conductive polymers, a special class of organic compounds that contain no metals but still conduct electricity thanks to carbon chain structures with alternating single and double bonds, allowing electrons to move smoothly along the molecular backbone. This factor makes the battery lightweight, durable, and environmentally friendly while maintaining high electrical transmission efficiency. PolyJoule's unique technology also lies in its entirely new electrochemical design. The battery uses 2 standard electrodes combined with conductive polymers and a non-flammable liquid electrolyte, blended from carbon and graphene. Its operation is based on the movement of ions between the 2 electrodes during charging and discharging. When charging, charged ions are stored in the electrode through an oxidation reaction. When discharging, they are released back via a reduction process. This mechanism is similar to what students learn in chemistry, but has been upgraded and applied on an industrial scale using much more advanced materials. Currently, the first customer using PolyJoule batteries is an energy company specializing in distributed systems. At the end of last year, this company installed the world's first industrial organic battery system at a dairy farm owned by the Fonterra Group near Hamilton, New Zealand. The system has operated continuously for 10 months to supply power for the milk processing warehouse. Fonterra plans to move this system to another location that frequently experiences power outages due to unstable supply. Thanks to PolyJoule's ultra-fast discharge rate, the battery helps maintain continuous operations, minimizing production downtime. Not stopping there, PolyJoule's super-fast charging capability opens potential integration into electric vehicle fleets, such as Fonterra's milk delivery trucks. Besides businesses, New Zealand's residents can also benefit from this technology. When PolyJoule energy storage systems are widely deployed on the national grid, wholesale electricity costs could be significantly reduced thanks to more efficient energy regulation. This is the future of energy storage, a solution that is sustainable, cost-effective, and safe for both businesses and households. What are the benefits of this new type of battery? PolyJoule is a promising battery technology with many advantages over traditional metal-based batteries. First of all, the production cost of PolyJoule batteries is much lower, allowing for easier scaling and wider accessibility. Specifically, the cost can be as low as $10 per kilowatt-hour, while lithium-ion batteries typically cost up to $100 for the same energy capacity. In addition, PolyJoule stands out with its high safety, as it does not pose the risk of catching fire like lithium-ion batteries, which can ignite at temperatures above 60 degrees Celsius. PolyJoule batteries remain stable and safe while operating in a wide temperature range from -40 degrees Celsius to 80 degrees Celsius without safety risks. From an environmental perspective, PolyJoule clearly demonstrates sustainability by using plastic materials that are recyclable or biodegradable, helping to reduce toxic waste. In contrast, lithium-ion batteries often contain heavy metals such as cobalt and nickel that can pollute the environment and negatively affect human health. Thanks to these advantages, PolyJoule is not just a replacement battery, but a significant step forward in providing more powerful, cheaper, safer, and environmentally friendly energy sources. It has wide potential applications, from phones, laptops, electric vehicles, to home energy systems, while also contributing to reducing dependence on fossil fuels and supporting the fight against climate change. However, the PolyJoule technology still faces some considerable challenges. The first issue is scalability. Although PolyJoule batteries can be easily produced on a small scale, transitioning to mass production requires optimizing and standardizing processes to ensure stable quality and performance. Additionally, supply chains and distribution systems need to be developed and expanded to meet the growing market demand. Another obstacle is performance. Although PolyJoule batteries have high energy density, their energy conversion and power delivery efficiency are still limited, especially since the voltage and output current are generally lower than those of existing metal-based batteries. Similarly, the energy conversion efficiency of PolyJoule solar panels is also inferior to traditional silicon solar panels. This calls for continued research to improve materials, electrode designs, and electrolytes to enhance overall efficiency. Why is Elon Musk particularly interested in advancing plastic battery technology? The industry and the original idea actually existed before Tesla even considered energy storage. Tesla's success comes from doing what is right for the environment and benefiting consumers. However, the materials needed for batteries remain a controversial issue. There have even been accusations of mistreatment of indigenous people near a lithium mine in Argentina. If this plastic battery technology proves to be highly feasible, Musk might get involved in the project. The idea of using plastic-based batteries for Powerwall and energy packs is quite appealing. Tesla has already started using lithium iron phosphate LFP cells in its megapack energy storage systems at the grid scale. Did you know that an electric vehicle battery pack can weigh nearly 900 pounds and directly affect the car's driving range? Plastic batteries technology is changing the game by cutting that weight by more than half, allowing vehicles to travel an extra 30 to 60 miles per charge, with the potential to account for up to 20% of global EV battery capacity by 2030. Are you ready to choose a lighter, longer range, and faster charging EV for your next car? Before we begin, please help us reach 8,500 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Model Q, Tesla EVs, and the latest news. How do plastic batteries reduce the weight of electric vehicles? Reducing weight is always a top priority in electric vehicle design, and nothing impacts weight more than the battery pack. Switching from metal materials to polymer-based batteries is a fundamental change. Without relying on heavy aluminum casing or metal frames, plastic batteries can cut 40 to 60% of the weight of the casing and core. For example, if a traditional lithium-ion battery pack weighs 880 pounds, its polymer counterpart weighs just over 440 pounds. This difference of more than 220 pounds can decide whether a vehicle travels 310 or 370 miles per charge. Weight reduction not only increases driving range but also triggers many positive effects: improved efficiency, reduced tire wear, lighter braking, and more responsive and agile handling when cornering or accelerating. A lighter car is always a better car without exception. In the electric vehicle market, this has economic significance. A lighter vehicle consumes less energy, charges faster, saves electricity, and prolongs battery life. However, what truly sets plastic batteries apart is their design flexibility. Traditional lithium-ion batteries are rigid fixed shapes, boxed structures, and inflexible. In contrast, plastic batteries can be bent, folded, or molded into any required shape. This is a strategic advantage. It allows automakers to make full use of every gap and space in the chassis. Instead of designing cars around the battery pack, now batteries can be designed to fit every curve, every floor layer, every small corner inside the cabin. This is especially important as the current trend in electric vehicles combines performance with aesthetics. For instance, the Tesla Cybertruck has an angular design, requiring the battery structure to be both strong and flexible, so it does not take up too much space. Future affordable models also need compact, lightweight, and easy-to-manufacture battery solutions. Elon Musk was not exaggerating when he said flexible battery design would be the foundation to optimize every millimeter inside the car. Flexibility also means scalable customization. Plastic batteries allow division into multiple modules, easy to integrate into robots like Optimus, small autonomous vehicles, or personal flying vehicles. This is something traditional metal-based batteries cannot achieve, and safety must not be overlooked. Plastic batteries have better heat resistance and are less prone to catching fire. CATL confirms that next-generation polymer battery cells can withstand up to 248 degrees Fahrenheit without risk of fire or explosion. For high-performance electric vehicles like the Tesla Model S Plaid or Roadster, this is a significant advantage. All these factors paint a clear picture. Polymer batteries not only help make vehicles lighter, they open a completely new approach to design, operation, and safety. It is predicted that this technology will account for 15 to 20% of global EV battery capacity by 2030, with a growth rate exceeding 30% annually. Tesla, BMW, and Hyundai are betting heavily on this. Elon Musk revealed that Tesla is testing polymer battery technology at Gigafactory, Texas, ready to integrate it into new generation vehicles. The shift to polymer batteries is not just a technical upgrade. It represents a production philosophy change, making batteries lighter, more flexible, and safer, so that the future electric vehicle is no longer just a replacement for gasoline cars, but a technological leap forward. At the current pace, polymer batteries could become the industry standard in less than a decade. And when that happens, Tesla, along with Elon Musk's vision, will not be left behind. On the contrary, they could lead the way. Once again, please help us reach 8,500 subscribers. This is important for us to stay motivated. Thank you. How do flexible plastic batteries optimize EV space? The electric vehicle industry has long been constrained by the physical limitations of traditional lithium-ion batteries. Although energy storage efficiency has improved significantly over the past decade, the rigid structure of cylindrical cells like 186502170 or 4680 or pouch cells has inadvertently shaped modern electric car design. Flat floors, fixed seat heights, and reduced cargo space are all the price paid for fitting batteries into box-like modules. Plastic batteries have reversed that rule. Thanks to their flexible structure and the absence of heavy metal casings, new battery cells can be molded into almost any geometry. Engineers are no longer limited to fitting batteries into block shapes, but can distribute them along previously unused spaces, such as gaps between double floors, door panels, seat frames, or C-pillars. This is no longer theoretical. Prototypes tested at the Osaka Institute of Technology in mid-2024 demonstrated that flat battery cells under 8 millimeters thick could be adhered to curved surfaces and operate stably after more than 2,000 charge cycles. This creates an entirely new design paradigm. For sports cars, seat height can be lowered closer to the ground since there is no need for a 12 to 15 centimeter thick battery module floor. For SUVs, or off-road, vehicles' battery architecture can be distributed evenly along the vehicle's horizontal frame, improving stability when climbing slopes or cornering at high speeds. Not only flexible plastic batteries also have slight elasticity following the chassis structure, allowing the vehicle to absorb impact forces better without causing internal battery fractures, according to crash tests conducted by TÜV Rheinland in 2024. Tesla is particularly pioneering in turning flexibility into a strategic advantage. In a leaked design from Giga Texas, a new affordable electric vehicle under development features thin-layer batteries shaped along the rear wheel arch and running down the door frame, a structure impossible with any traditional battery type. As a result, total battery volume can increase by 12 to 18% without extending the vehicle's length or height, a crucial difference for models targeting urban markets where every millimeter of space counts. Notably, this flexibility also paves the way for a completely new concept: the vehicle frame integrated with the battery. It's no longer simply placing the battery inside the frame. Polymer batteries can now become part of the chassis, serving both as a power source and as a load-bearing structure. In load tests at Stanford University, in late 2024, a carbon fiber-wrapped polymer battery pack withstood compressive forces exceeding 3,500 newtons without deformation, 28% better than traditional load-bearing aluminum frames. This opens the potential to eliminate a significant portion of metal materials, reducing weight and lowering production costs by 9 to 12% per vehicle. Another critical technical improvement is eliminating the need for liquid cooling systems, which typically account for 7 to 9% of the total battery system weight. Due to lower current density and more even heat distribution across polymer cell surfaces, maintaining stable temperatures becomes simpler. Real-world testing at Magna Steyr showed that under continuous operation at 120 kilometers per hour for 2 hours at 35 degrees Celsius ambient temperature polymer batteries only heated up by 8 to 10 degrees Celsius without active cooling. This not only reduces vehicle weight, but also removes risks of coolant leakage or electrical short circuits issues that have caused controversies in many premium electric vehicles. For modular vehicles or small two-seaters like Tesla Pod or shared urban electric cars, flexible battery architecture is essential for volume optimization. Without fixed battery blocks taking up 30 to 40% of the vehicle floor, designers can place batteries outside the pillars integrated into doors or seats, creating more spacious interiors without compromising performance. From a static component, polymer batteries are becoming a factor that reshapes the entire design philosophy of electric vehicles. Instead of designing cars around batteries, batteries can now follow the shape of the car, bending, pressing, adhering, and folding according to engineers' intentions. This is a quiet revolution, but one that has more structural disruptive power than any technological change in the automotive industry in the past 20 years. How does polymer material extend the lifespan of electric vehicle batteries? Extending battery lifespan is one of the biggest challenges in the electric vehicle industry today. On average, traditional lithium-ion batteries in electric cars last about 1,000 to 1,500 charge-discharge cycles, equivalent to 8 to 10 years of normal use. After this period, battery performance significantly degrades, forcing users to replace the battery at a very high cost, usually ranging from $7,000 to $15,000 depending on the model and battery capacity. This poses a major barrier for average consumers, especially in developing markets. Meanwhile, polymer batteries, also known as conductive plastic batteries, are showing outstanding potential and durability. According to PolyJoule, a pioneering company in polymer battery technology, their products can reach up to 12,000 charge-discharge cycles while maintaining over 90% efficiency. This means battery lifespan could extend up to 25 to 30 years, far exceeding the lifespan of the electric vehicle itself. Even after the vehicle's end of life, the batteries can still be reused for stationary energy storage systems, such as charging stations, home grids, or solar power storage. From an economic perspective, this difference is highly significant. If a lithium-ion battery pack needs to be replaced after 10 years at a cost of $10,000. Then over a 30-year lifespan, users might spend up to $20,000 to $30,000 solely on battery maintenance. In contrast, polymer batteries almost entirely eliminate replacement costs, helping users save tens of thousands of dollars and greatly reducing industrial waste. Not only does polymer battery extend lifespan, but it also offers advantages in design. Unlike rigid and heavy lithium-ion batteries, polymer batteries have a flexible structure that can be bent or shaped to fit the vehicle frame. This opens up possibilities for electric vehicles with lower center of gravity, better weight distribution, and optimized interior space. Tesla is actively researching integrating this technology into next-generation models, such as the affordable Tesla Model 2 and special sports editions like the Roadster Space X. Regarding weight, polymer batteries also show significant potential. PolyJoule claims their batteries have lower energy density compared to lithium-ion batteries, but the overall system weight is substantially reduced by eliminating complex cooling systems. This helps reduce vehicle weight by 10 to 15%, translating into a 5 to 10% increase in driving range per charge. For ultra-light vehicles like Tesla Model 2, this could be a decisive factor in maintaining a price below $25,000 while ensuring competitive performance against gasoline cars. Additionally, polymer batteries are non-flammable, non-explosive, and operate stably within temperatures ranging from -40 degrees Celsius to 60 degrees Celsius. While lithium-ion batteries are prone to damage or performance loss at extreme temperatures, polymer batteries require no cooling or heating systems. This not only extends battery life but also reduces production costs and increases safety, especially critical for autonomous vehicles or robots like Tesla Optimus that demand highly durable and safe battery systems. Elon Musk once stated that battery lifespan is the final barrier to a future where electric vehicles can last 30 to 50 years and be passed down across generations. To achieve this, he has heavily invested in researching new materials from silicon to lithium iron phosphate, but polymer batteries could be the true breakthrough. Although polymer batteries currently have lower energy density than lithium-ion, about 150 watt-hours per kilogram versus 250 watt-hours per kilogram, rapid technological advancements are expected to close this gap within 3 to 5 years. Tesla has not yet announced any vehicle line using polymer batteries, but supply chain reports indicate Tesla has filed patents related to polymer-based electrolytes and is testing flexible battery cells at Giga, Texas. It is predicted that the affordable Model 2 or commercial versions of the self-driving robotaxi will be the first platforms to trial this technology, where low cost, long lifespan, and high safety are top priorities. Finally, from an environmental standpoint, using polymer batteries lasting up to 30 years reduces battery waste by 70 to 80% over the product lifecycle compared to traditional lithium-ion batteries. Moreover, many polymer batteries are made from materials free of rare metals like cobalt or nickel, lowering dependency on mining and lessening impacts on global supply chains. Compared to lithium-ion batteries, polymer batteries increase lifespan by 3 to 5 times, drastically reduce replacement costs, enhance design flexibility, lower weight, improve operational efficiency, and boost safety. With the global electrification trend, this represents an opportunity for Tesla and other manufacturers to reshape electric vehicle architecture for the future, from supercars to mass-market cars, and even robots and electric aircraft. We appreciate your contributions and hope you will have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Techno Creator family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Thank you so much for watching, and we'll see you soon. Until then, stay safe and have fun.